Let's see. Please feel free to ask questions. Just toss them in the chat. Actually, you can go ahead and interrupt me too if you want. Um, I'll share my screen. I have a bunch of PowerPoint slides. But as we were just talking about, PowerPoint slides are, I mean, they provide a way to have like information that we're sharing, but a lot of this is just about this talking. So I'd really rather just answer questions. Like somebody, before I can explain what these different pictures are, like my background is the Soar Telescope. So what I do, in practice now, I'm department chair, and the physics astronomy is a big department. So actually I spend a lot of my time doing administrative stuff. But before that, for most of the previous few decades, I studied astronomy. And so I'm in the astronomy part of the physics astronomy department, and part of that's using telescopes. And so the one in the background is a Soar Telescope, which is in Chile. And it's one Michigan State owns part of. We actually sort of more or less own a seventh of it. We share it with a few other places, North Carolina, the country of Brazil, things like that. I'll show it at the end, especially if you ask. We actually can use it from the first floor of BPS. So when we had in-person classes, how many people walked through the atrium of BPS? Okay, yeah. So that little room next to 1410 is the SOAR observing room. And the computer, you probably just walked by it and never noticed it. But they had this idea that that this way all the people are in BPS, which in a regular time is a lot, right? Could then see us using the telescope. But the problem is that we observe at night, and Chile's roughly in the same time zone we are. So the main people who see people using the telescope from there are the custodians working late at night. And we also don't get every night since we own about a seventh of it. We mostly do that. You can actually go there. I've done that just a couple of times. In the old days, very reliable internet, part of being an astronomer was actually flying around to actually be on site more. That's not so true anymore. Okay, and then what are these pictures? So my research was over the years been about black holes and globular clusters. So at least you probably heard of a black hole. They've been in the news in the last few years more for two reasons. I'll talk. One of them is about when we've actually seen the gravitational wave signatures emerging black holes with this thing called LIGO. So that's, I will talk that's what the picture on your left is supposed to be. I will talk about that some. Unless you happen to be an astrophysics major, you probably don't know what a globular cluster is. So I'll talk a little bit about that too. That's the picture on the right. Each one of those little dots is a star. That's and a globular cluster is basically a gravitationally bound together dense collection of about 1 million stars that all sort of form together all in this really dense place. They're like the urban centers of the galaxy. And I've studied those a lot in my career, and I'll talk a little bit about why these two might be connected. That's sort of the main point. Okay. So with the one of the main things I've been interested in last couple of years, so it sort of helps me sort of decide your science question, right? So, and this may all sound a little bit gibberish, but so I'm interested in whether black holes merge in globular clusters. And this became, I've studied different parts of this problem over a long time. And it sort of crystallizes, this is the main question I'm doing now, partially because this thing called LIGO discovered black hole mergers. And that was in the news a few years ago first, and now it's still going. And I'll describe a little bit in case you missed that news, or there's been so much news since then that you forgot it. But it showed that these black holes really do merge. So it's just sort of cool, if nothing else, right? So not only is there really a black hole, but then they really actually sometimes get so super close together that they coalesce into a new black hole. So that sort of leads it to the question, how do you even make black holes in the first place, right? Now, if you took ISP 205 or AST 207, you should know the answer, but you might not remember. So we'll go over that so that's basically the end of a life of a massive star. They can end as black holes. We actually think we understand that part, but what we don't really know is how you get the black holes close enough to each other to merge. And so one of the reasons it's not really science, it's not really research if you actually already know the answer. And so one of the cool things is that we really don't know. We've seen them merge, but they're actually two competing theories about how you get the black holes close enough together, and we don't know which one's more correct. And one of them has to do with globular clusters.
What's the other one?
The other, okay, it's sort of skipping to the end, but it's a good question. So the other one is that they're basically born together, like they're born as a pair. And then they both go you get two massive stars are formed together, and then they both have their evolution to end up as black holes, but they somehow stay during that process, and actually get even closer together. And that's not easy to do. When I describe what happens at the end of life of massive stars, you can see why it's not that easy to do. And I'm sort of giving you a lot of the answer at the end now. And then, so it's not, we know stars form in pairs a lot. The sun is actually, there's basically almost, roughly speaking, as many stars have formed in pairs as they are by themselves. So the hard part, though, is after all, they do all their stuff going from their birth to the end of their life, how they get really close together as a pair. The globular clusters, the stars all form separately, but they're all close together. And then all the stuff, all the messing around between them being really close together then the question is whether that can cause two of them to actually get super close together, a lot more closer than average, basically almost running into each other. It's a little bit like whether the best way to pair up is to put yourself in a big city and just run into somebody, or to be sort of, born right next to somebody, somewhere else. And that's not really a great analogy. And which one of those is the most, which one of those two has caused the most of the LIGO sources is really still an active question. And I could get two famous astronomers in here who would say the other folks are just wrong and they're right with their answer. I've taken a more what we would call an astronomy observational approach to try to, and really all I've at this point am trying to do is, you'll see, I'm giving a lot of the answer ahead of time, is establish that there really are black holes and globular clusters. That's actually not been established. We know there's some black holes around, but we don't really know that they're in globular clusters. I'll try to describe a little bit why it's not so obvious. That gets a little more technical. So there you go. That's at some level, one of the reasons this one I sort of ramble. One of the reasons I ended up in astronomy, because I was just like a regular, like math and science kid, so to speak, when I was undergrad, is that the questions could be posed in a way that I could understand the question pretty early on. And I liked that. So anyway, I'm not even sure that's true anymore, but it was true way, way, way back when I was doing it. Okay. So first, I'll say a little bit about LIGO. It's not so new anymore, but there's something still really cool about finding gravitational waves to me. I mean, if you're on that, I'm sort of assuming if you bother to show up for this, that the sort of science research bit has some interest to you. So I'm sorry if it, if it doesn't. But so I think and so it's essentially, it's a giant, basically what they call an interferometer, and it more or less takes a laser and shoots it down. See this, shoots into, it takes a laser, shoots it this way, splits the beam this way in this way, and then when they bounces back from a mirror, and then it recombines it, and it uses the wave properties of light. So if the distance is exactly the same, it'll constructively interfere, and if it's slightly off, it'll start destructively interfering. And if you get a gravitational wave that comes through, it distorts the space-time along one arm, but not the other arm, because notice they're parallel. I mean, sorry, perpendicular. It distorts one arm differently than the other arm, and you get a you see the difference in the distance by the fact that now the laser is traversing a slightly different distance one direction than the other. And it's insanely difficult because these are like 4 kilometers, and the tolerances are just really, 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 really tight. And it basically took like 30 years of doing it to get it so they could be sensitive enough to the effect of it's something like, I think I have the number somewhere. This wasn't originally not a technical talk. It's something like 10 to the minus 21, if I remember right. So it's just super, super hard. And there were people who spent their whole lives working on it, more or less. It really was like 30 years. Another reason I did astronomy is the projects tended not to be that long. So, okay. So there were the original LIGO just got all upper limits. Science was sort of boring that way. And so the first one was now a little more than 5 years ago. And then this is how they reconstruct it. The gravitational wave, because notice the times are really short. And then the frequency of the distance changing gets high. This is as the black holes get really close together, they're sending out wave, they're basically distorting space-time with a frequency that's the orbital frequency of the binary black holes, which is then, gets up to 100, close to 1,000 hertz. And at that point, they merge. There's 2 of these thingies like this, one in Eastern Washington and one in Louisiana. They're partially put there to be sort of in the middle. Oops, sorry, middle of nowhere. Because like even if a truck drives by, the vibrations cause the thing to jiggle, and so they really have to be really isolated, really in the middle of nowhere. I don't know if I have the pictures to show how middle of nowhere they are. This is a former nuclear reactor site, and I think this was in Louisiana, partially because they also have to be seismically quiet. Not much happens in Louisiana, but also I think there was some politician from. So this is the strain. This is basically what we're measuring. So yeah, it's super small. Then they reconstruct it and blah, blah, blah. So I did nothing to do with any of this part. This just to show it happen. Like I said, there's some very, in fact, so the people who did this, it's Nobel Prize winning stuff. But there was really a large group led by a few people. So it really happens. And then to some extent, the amazing thing is it kept happening. So this is the first, that happened to be the first one. And you can, by modeling those things, they can get really detailed information. Like one of the black holes was 36 plus or minus this times the mass of the sun. The sun's mass is a typical number to use for these things. The other black hole was 29 plus or minus 4. So the final black hole mass was this. The final black hole mass is a little bit less than the combination of these two. And that energy is what gets released. So it's really an enormous amount of energy that gets released. This is when E equals mc squared really works. So if you think about E equals MC squared rarely actually comes into play in any applications, but it really works here, and it really does convert several times the mass of the sun into energy in a very short amount of time. So basically, in a fraction of a second, it's 100 times all the energy that'll ever be produced by the sun. So it's an enormous amount of luminosity that goes out into the strain, this strain in the space-time wave that goes by. And so partly because it is so luminous, we can see it a long, long way away from us.
I have a question again.
Yeah.
So how does the wave or the gravitational wave get beyond the gravitational pull of the black holes?
Let me see if I have a picture. So it's not, the black hole is strained. I don't think I kept the picture. Let me actually go back then. So the event horizon, it's basically the black hole has a strong warp space-time strongly outside, not just inside of the event horizon, but outside the event horizon. So if you're outside the event horizon is like you're inside that, you're inside the black hole, and information never gets out and it's done, right? Yeah. So if you're just outside the event horizon, the space-time is highly distorted, but you're not, but you can, the information can travel outside of the black hole.
So the waves really come just from right outside and close to.
Well, yeah, that's right. So that's why it's drawn like this.
Okay.
And then the modeling, and what happens is, of course, the black holes were farther apart, and their distortion of space-time wasn't zero. It was just a lot smaller. And then it only gets big enough for us to see when they get really close. And it's still, I mean, it's still small. But it is the simplest way to think about it. It's the same reason we can see any effect of black holes on space-time. There are other ones called like lensing, where the light waves get bent around the black hole, and it's because the space-time is, I don't have the picture of the like bowling ball in the plastic sheet, but the space-time gets distorted even outside the event horizon of the black hole. And then that, it's essentially, the distortion create ripples as the two objects get closer and closer together, because it's essentially, it's really in a different context, it's really just a dipole, it's distorting it asymmetrically, and you get these ripples.
Thank you.
Yep. Okay, so it releases a ton of energy, travels all across a billion light years, has some small effect on Earth. Of course, so now let's see, it's found a lot more than several more. There's like over 100 now. It just keeps, when they've all been operational, it's basically been finding one a week, which is just sort of amazing. And one of the aspects of that is actually it's a higher rate than anybody predicted. So this gets into the question of where are they coming from. So the initial predictions were that it wouldn't see so many. So there are more emerging black holes than what people were willing to predict before the experiments went live. This is the original LIGOs. Science of this kind is a very international deal. So these are the two LIGOs. Then there's a Virgo, which is the European one that's operational. I don't actually know much about this one. There's going to be a LIGO India, where basically they're taking all the leftover parts from LIGO and putting in building one in India. There's a Japanese one that is moving along called Kegra. Oops. And it helps for directionality to see where in the sky and therefore where in the universe it happened, to have more of these sites going, because then you can reconstruct where it came, the direction it came from better. So that's been going on. So here is another, oops, let me keep an eye on the chat.
There's
Oh yeah, no, it's the same reason that like there's a lot more. I mean, no, it's because these are expensive to build. It would be useful actually to spread them out in all directions. If you did this with optical telescopes, like the ones where you look at visible light through the the light comes to the atmosphere. In fact, the largest number in the world are in Chile, right around here, where Soar is, and that's because there are aspects to locating it it's basically in the foothills of the Andes. Those are in the foothills of the Andes, and that's just the best place in the world for those. And so that's where most of them have gone. The other main place they are is in Hawaii. Actually, you can see the Hawaiian Islands there. It does help to have some in the north and the south. If you want to monitor something 24 hours, it helps to have it across the globe in this direction. But there are some things you can only see with visible light from the northern hemisphere or the southern hemisphere. So there is some reason to spread it that way. The gravitational waves just go right. They don't care about the Earth. So you don't need, you don't have that issue, but you do sort of want to spread them out. So the main reason is these are expensive to build. And so nobody's built one in the southern hemisphere. Let me keep up with the chat. Yeah, the way they I'm actually not an expert in how they reconstruct it. I think it's more the timing than the distance, than the magnitude, than the strength that determines the location. And so, but I'm not an expert on that. So I'd actually need to look that up to be sure. It's a good question. A lot of it, they're not all equally sensitive. So they sometimes if it's a weaker signal, it won't show up on all of them, even if it's real. Okay. This is several years old, but one of the other things that has happened is that the black hole masses are sort of high for a typical stellar evolution model. And they tend to be, this is all in terms of the mass of the sun. They tend to be up here. Things below about 2 solar masses and below are neutron stars and not black holes. There's this one, I don't think there have been any others. I haven't tracked this really carefully lately. There's this one that's in like the intermediate range where we're not sure whether it's a heavy neutron star or a light black hole. There seem that it's easier to see the more massive ones, but that doesn't seem to completely explain why we don't see more down here from the mergers. So basically, if you have 2 bigger ones merged, then there is a dependence of the signal on the mass, but there should still be more that aren't quite as massive, that are maybe a little closer. So the signal more or less depends on the mass and the distance. So anyway, and then there's plenty of neutron stars. So yeah, this one's pretty interesting. Exactly what happens as you push the neutron star limit starts to overlap with the physics that the nuclear physicists over at FRIB do, for example. Just since we're here at Michigan State, I'll bring that up. Okay. And like I said, LIGO's found a lot more since then, and I did not update this slide. Okay, so there really aren't many down here. And so what happens is the rate down here is what people more or less expected, which was not very many. And the rate up here was it was what, surprisingly high. And it's not that they don't happen, it's just that they're really rare. So black hole mergers leave no trace. If if they really do, there's a new black hole. So the other thing that happens, and one of the main giant sort of things is, so if you have two black holes and they merge together, you just get another black hole. If you have two neutron stars that merge together, then you have regular stuff merging. So even if it goes on to make a black hole, you get all sorts of exciting nuclear physics going on with the nuclear matter that you don't get if you had two black holes already. And from studying, there has been one really good case of a neutron star merger. Oops, I'm not going to say anything more about that. There was one really good case of neutron star merger, and then modeling that, which included different people here were involved in different ways. Modeling that really argued that neutron star mergers were probably the source of a lot of the heaviest elements in the periodic table. So that was cool. But they're really rare to see with LIGO because the signal depends on the masses and they're not as massive and they don't happen that often. But we're able to see it because there was a neutron star merger, and that makes the light, because when all that stuff that happens together can make light that we can then go study. When you have the black hole mergers, they're just black. And all you see is the gravitational signature. And people spend a fair amount of optical telescope time just checking and looking to make sure, but yeah, they really were black. Okay, so how do you make black holes? I'll do the how do you make black holes, and then how do you get them to merge? So we mostly know the first one. There are people here who study that, how to blow stars up, basically. So this is stolen from an ISP and AST 207 slide. It's all nuclear physics. Basically, a star is something that's hot and dense enough at its center that it can do fusion. A really cool thing is that, fusion has off and on been the one of the sort of things people want to do, right? If we could get a real fusion reaction going, it would solve all our energy problems. But it's really hard because it's hard to keep it confined. It gets hot when it really hot plasmas don't like to stay all dense and compact together to keep fusing. So there is supposedly a couple of new ideas about how to actually do that. So we'll see. One of my favorite questions when I would teach ISP 205 was, if fusion is such a great way to make energy, why don't we do it on Earth? But that's what a star is. That's how a star shines. It essentially shines because it's got a fusion reaction going on at its center. The sun will not, then the more massive a star is, the more it can compress the center to fuse heavier and heavier elements together. Turns out that iron can't be, is a dead end in nuclear physics. Fusing iron together to heavier stuff doesn't get you any more energy. It gets you less energy. Iron is the minimum. So once you get an iron core, it's inert. You still have all the gravitational pressure from the rest of the star pushing down on it, but iron core doesn't want to get compressed anymore. There's this bounce back and you get a supernova explosion. Now there's a lot of stuff just encapsulated in this statement here. So this is Professor Sean Couch's, for example, whole research program is in these this one sentence. So it's, depends who you're talking to, which part they talk about the most. So if you had Professor Sean Couch on here, he would then, it's all about, so they use, this part is modeled with, I'll just throw these other things out there. This part is modeled with the largest Department of Energy supercomputers. So there's a whole specialty. And then if you really ask this, you guess your recording's okay. But the real reason the Department of Energy cares is because it's a lot like a nuclear weapon at that point. But it's also really cool that it's also how supernova work. So then it blows up. You see the results in the sky. And all the outer layers get thrown out, and then there's all these elements that get incorporated into new stars, and then that's one of the main ways where star stuff is. The universe starts out with not very many of these elements, and stars blow up, and the elements from those blown up stars get incorporated in the rest of the stuff that makes new stars, and keeps going on like that for generations and generations, and you end up with us. What's left behind from the supernova is either a neutron star or black hole. And so actually one of the recent one of these that was really close was supernova 1987A, which was in a near sort of like a satellite galaxy to our own. And so when it blew up, it was a naked eye object in the southern hemisphere. And so you can see that we know which star blew up, and then it did this, and then it disappeared. And there's either a neutron star black hole there, depending on all sorts of stuff, probably the mass of the star and things like that. So it's not just that computer models sort of show this. We see stellar mass black holes because sometimes they're in these wide binaries and there's a star orbiting around. And then we can figure out by just Kepler's law that there's something sitting there that's more massive. We can actually do this with the center of the Milky Way galaxy. You can see stars orbit around the center of the Milky Way and figure out that there must be a black hole of a few million times the mass of the sun there. We actually have traced the whole orbit out, so you really can do Kepler's law for real. It's sort of fun. But this is what I said at the very beginning, we have no idea to keep two massive stars bound together, so you get a close binary black hole system, and the LIGO masses are also higher than the known stellar mass black holes. And the problem is that these things are really rare. There is one really close neutron star pair known in all of our own Milky Way galaxy. So the issue is that we can see these merging black holes out to billions of light years, and in billions of light years there's hundreds of millions of galaxies. So you have the challenge of dealing with rare events, and so that opens up the possibility of lots of sort of strange pathways to get to rare events. Yep. Go ahead.
Is there anything else that might cause these gravitational waves that we could be confusing?
Yep. Good question. So this is where there's a whole specialty also using supercomputers. I'm going to skip back a lot of modeling what happens when, where am I? It's modeling what happens when you get two black holes. So you take everything we know about general relativity and you do this, and the calculations are really hard because it's not a symmetric problem, and general relativity is actually a bunch of complicated equations. And then they specifically predict these. They say if, they've run lots of different models, and this is what the little red line in numerical relativity and reconstructed. So it really works pretty well. Now they have to do, that's one of the reasons there's two sites though, is like if there's like some just seismic activity at one site it shouldn't be in the other one and things like that. And now there's 3 or 4 sites. And in fact, one of the things that's sort of funny, most of the people who started doing this hope to test general relativity at its sort of really strong points, when it's really, really strong. In fact, general relativity works great, but we had already tested it in a lot of other ways. And so if it hadn't worked really well, which is basically the how well the bottom lines line up, people would have not really suspected that general relativity was wrong, because it's worked so well in other ways. What it really has, it's sort of funny, but it's extraordinarily interesting for astronomy, because it's like, well, how in the world do you get these black holes together to merge, right? We've really seen them merge. So that's like the astronomy part, is like, how do you get the black holes together to merge? The sort of traditional physics part is general relativity really the right description of gravity and space on these scales? And of course they go together. And it's also the astronomy part, is when we found the one case where we saw the 2 neutron stars merge, it really explained a lot of where some of those elements came from. So there's a whole bunch of testing. In fact, there was one group that claimed that the LIGO people had misinterpreted their time signals along this way. So there's a whole bunch of basically nitpicking and back and forthing, and it's really comes out to be really pretty solid. The other thing that they do, and I'll just sort of explain this, but how science works, is in this big experiment, before they found one, they would, to test whether people who were analyzing the data in pseudo real time were doing things correctly, they would inject things into the data stream, basically, fake signals, and see what people would get out, and test whether they were getting out what they thought they would, and things like that. So there would be these, and then they had specifically like limited, like only 3 people would know that this happens, and then I guess it had to be more than one in case something happened to them. But they were really, because I mean, it's a little bit where extraordinary claims require extraordinary evidence, so they really knew that the first ones had to really be solid. But that's right, it's a good question. And when you give these talks, you sort of gloss over, I mean, there were, like I said, there were thousands, I mean, actually, there were more than thousands of person years to go into all that kind of stuff. So it gets sort of glossed over, and answering that question, like what else could do this, right? How are we controlling for all sorts of other things, was definitely a concern. Now with multiple different detectors and all this, it seems to be pretty established.
All right, thank you.
Yep. Okay, so we get black holes. We don't know how to get them together. So I'll try not to go too long. So here is another picture of a globular cluster. They tend to be old. They're even by astronomy terms. And these stars are all moving around. Basically, their motions are determined by the average gravity of the rest of the stars here. So they all move around in this like little group, and they're all close together. It's like the it's like the Manhattans of the universe pre-pandemic. So there's all the average distance between the stars here is the average distance. The star nearest to us is a few light years away. Then here it's a few light weeks away. So they're all really close together. Here we go. Hundreds of thousands of stars in very compact region. They're all bound together by the gravity. They form together in small volumes. They're the same age and elemental content. Then you find these everywhere. Oops. Okay, in our galaxy, you find them out here. Okay, I'm not going to do that. There's a zoom in, but okay. we're going to skip that. Come on. This is, now I'm going to get to what we do. So here's one. And so this is a famous galaxy. It's a cool looking galaxy. And all these little dots, let me see if I can go back, skipped over there. See all these little dots here? I don't know how well it really is coming across. Each one of these is a star cluster of about 1 million stars around this other galaxy besides our own. So the universe has these vast scales. You just get used to it if you do it. So we have like our own Milky Way galaxy where there's maybe 10 billion stars, and we maybe have hundreds of these globular clusters, each with 1 million stars. But then there's millions of galaxies, and then they each have thousands of their own globular clusters. So the numbers get really big. And that means you don't need a whole lot of these events to be happening there to get to see something. Okay, so, and then it's true. Oops, I moved this. It's true for the next one too. Same thing here for this galaxy. Each one of these little dots. This is an artist rendition. We didn't really do this, but this is what one of those globular cluster pictures I look like. Each one of these is one of those. So the question is, in all these thousands of globular clusters around millions and hundreds of millions of other galaxies, do every once in a while, the two black holes in these dense regions get so close together that they merge? And that's really what we're getting to. And so there's all sorts of sort of interesting / weird physics that goes on when you have all of these really high density of stars. So the stellar evolution itself works pretty normally. So stars fuse hydrogen in their centers, and if they're massive enough, they'll fuse other elements. And the more massive they are, the faster the evolution happens and things like that. That's all pretty typical. They're closer together, though. The typical separation is a few light weeks instead of light years. Their motions are all dominated by the gravity of the other stars, which is not true of the sun. All the interactions between them cause the heavier ones to sink to the center, the lighter ones to go to the outskirts. Eventually they dissolve because this keeps happening. The lighter ones go to the outskirts or leave the system, the heavier ones sink. So at some level, eventually the clusters will all dissolve with just a few of the most massive stars left at the center. And that's what this is a long time ago now, but I wrote an article for Science where and the whole cluster is on the brink of collapse because the massive ones keep going to the center and the lower mass ones keep leaving. And then after those lower mass ones have left, the next set of lower mass ones then starts leaving. Eventually it all goes away. Okay. And so one of the things that happens when it's doing this is the stars are still close together and they run into each other. And as all this is happening, you get all sorts of weird things happening with the stars that you don't get if they're all off by themselves. So less than 1% of all stars are in globular clusters. But if you look in a X-ray eyes at our Milky Way galaxy, half of all the X-ray emitting binary stars are in globular clusters. So these things are where neutron stars are black holes that are accreting matter from a companion. So what happens is you say, okay, well, what happens when all these stars are all getting close together and all messing around in the center and all this? Well, when we look at X-rays, we see that if you look at things that are glowing brightly in X-rays, a lot of those, there aren't that many of those kind of stars, but the ones that are tend to be in these densest regions. So up to 50% of the X-ray binaries are in globular clusters, where only 1% of the stars are. So what's going on there? Where's the picture? Oh, come on. Did I lose that picture? No, it's here. Hold on. There we go. Sorry. This is what's going on. You have a regular star and and here is your neutron star black hole. In this case, it could be a white dwarf. And the gravity from this one, which is really strong because it's actually a lot of mass in that small region, pulls the stuff from the outer regions here. Because if you put yourself as a particle here, the gravitational pull from here is actually more than from here. You flow in this direction. However, there's probably just a little bit of angular momentum, so you don't go exactly 100% this way. If you're just angled off a little bit, you end up in an orbit. And then instead of swinging all the way back up here, there's some friction. You run into some other stuff here, and you settle into this disk. Now, you're really close to here, so your potential energies, you're really high. You're moving really fast, and friction causes this disk to heat up. And if something is really a gas is really hot, and it's gonna, when it emits, it's gonna emit in X-rays, and so you get X-rays from the material not on top of the black hole or neutron star or even white dwarf, or really close to it. And so this is what we see when we look at with X-ray eyes at our galaxy. We see cases where this is happening. And then that's one of the ways we can infer that there are really neutron stars or black holes, because the stuff's falling on so much, it sort of has, you need a super dense object sitting there at the center to be what's called accreting this material. It's glowing really brightly in X-rays. Can't see that with an optical telescope. You can see that with X-ray telescopes. And so then we can see that. So that's one of the ways that we know that globular clusters are special, because we see this happening. Now it turns out, I'm going to zoom way back. It turns out that the 13 best cases in the Milky Way globular clusters, our own galaxy, are all neutron stars, because they all have a surface and they're not black holes. So are there no black holes in globular clusters because they don't stay there? They all get kicked out? Or is it because we just don't have that many Milky Way globular clusters to look at to happen to have one accreting now? And that's sort of where the whole question gets down to, based on the time. And so I was doing some of this before LIGO came along at all, just wanting to understand some of the objects that we were seeing in these globular clusters and these interactions between the neutron stars and maybe black holes and the other stars. And then LIGO came along and we're like, oh, well, if there are black holes in globular clusters, this is really important. I'm going to skip this one. And so then it was like, well, now it's in all of our things. I was to say a little bit about how we do this. So do black holes merge in globular clusters, and then possibly, and if so, they could be the major sources of gravitational waves. So I was this is like our favorite one that we study. And I was able to name it after one of my grad students, Kathy Rohde, and myself. So that was cool. I'll throw one at Arden's mom used to say, oh yeah, you've discovered a black hole. When she would meet me, she thought that was really funny. Sorry, Arden, but I have to say that.
That is pretty cool,
though. It was funnier coming from her. So I was skipping way ahead, right? So because it's time's short, so how does this like work, right? So I wanted to talk a little bit about the telescope. So this is the Soar Telescope. So what happens is there's this combination of, I don't have a picture of the Chandra X-ray telescopes. We use all these different telescopes. I gave you like the LIGO, but how do we find out where the X-rays are coming from that might be the black hole? Or how do we find like that picture I showed? How do we do this? So we often combine like X-ray telescopes and then visible light telescopes. And an X-ray telescope has to be a space telescope because the X-rays don't get through the atmosphere. But if you look at visible light, then we study different things in visible light, and we do that with the Soar Telescope. So I wanted to come back to that since that's our telescope. And then you have these ideas about the science question you want to answer, and you write proposals, and sometimes your proposals get accepted. And then you get data or you get funding, and then there's those kinds of things that if you just wonder how the research enterprise works, and that's part of it. And that's a little bit broadly true across disciplines, even with physics or even chemistry, engineering, those kinds of things, probably even life sciences as well. So I really jumped way forward here. But it really gets down to I sort of establishing the big picture about why do we want to, why might black holes and globular clusters be interesting? Then we have to figure out how do we really find one? And that's the hard part, which I sort of skipped over pretty fast. And then what happens though is we think we found a good case in one of these little objects in this galaxy, and then we go off and this is one of the things we observe with the Soar Telescope. So you use telescopes to collect light and they're bigger. This is just pictures. This is a picture of the telescope. So why is it on a mountain in Chile? So it's, oh shoot. It's on a mountain in Chile. That slide got lost. There we go. It's on a mountain in Chile because the smooth air off the Pacific Ocean, it's both clear. No, it's nice and clear. Sorry. Nice and clear. And then the airflow is really smooth, so you don't get a lot of atmospheric distortion. So how do you start? You have a science question. We want to know what's going on to possibly accreting black hole. Are black holes common in globular clusters? Do they grow by accreting other stars? Do they merge? So why is the mountain in Chile? This is out of order. Clear skies, also dark skies, smooth airflow. There is actually a campus observatory. How many of you know where the campus observatory is? How many of you have been there? So we hope to reopen by the summer, or hopefully, pandemic permitting. Michigan does not qualify for very many of these things at all. Clear skies, definitely not. Dark skies, if you've been to the campus observatory, the pavilion is like right there. Smooth airflow, definitely not with all the humidity. So yes, Michigan, not ideal for ground-based astronomy. That's why we have it in Chile. Anyway, yeah, cool pictures like this. Really, though, what we were doing, this is the last thing, is we want to take a spectrum. So we actually have a thing that we take a grating, which is sort of like a prism, divides the light up in its component parts. And then we look to see if it's like that, and we get something like this. This is what a proposal looks like. Spend a lot of, this is what our observing schedule, I pulled this in 2017. Okay, there we are. Well, like 20 years ago almost. There's the telescope. This is what the data actually looks like. You spend an enormous amount of time in front of your laptop manipulating the data to remove all the instrumental signatures. This is a little blip is what we cared about. And I think I'll stop there. And then you get this. Then you publish the paper. And then that's that. So we'll go back to the pretty picture and stop and take questions. Thanks for listening.
Thank you so much. That's really interesting. So yeah, does anyone have any further questions or questions from both before and the slides? Feel free to ask.
Or about anything else, just about anything sort of works really broadly. Because I know Zip through at the end, but
yeah, I wanted to ask something. So it's, can you hear me?
Yep.
Yeah. So it's a bit off on a tangent though. So here we're having a wave incident on the Earth, and we're checking for deflection in space-time and all. When it is instead of, say, a shower of particles, like if the thing were a little more particular than wave-like, as in here, like say when neutrinos come or something like that, how do we measure the like the direction and velocity of it? when
Okay,
it's,
yeah, I'll give you one. There was the one case where so one of the problems with the black holes is they don't do any of the rest of the stuff with regular matter. But we did see the case where two neutron stars merged, and we saw both a light signal, because when there was lots of cool nuclear physics going on, making all the kind of things, other stuff, like there was a light signature. If we had sensed enough things, we would have seen a neutrino signature, for example. We didn't, but we could have. So we saw a light signature and the gravitational wave signature from the same place. This gravitational wave thing wasn't localized all that well, but when we looked for something in light that changed at the same time as the gravitational wave, and eventually people tracked it down, it was really cool. And so we pinpointed where that happened. And in fact, you can tell that the light travel time and the gravitational wave travel time were basically identical to our ability to tell. And so, and then you can sort of model how that worked, which one happened exactly, first, because we did actually, so in some sense, we did see a case. It wasn't the black holes, but it was the two neutron stars merge, where we saw both the distortions in space-time and the light signature from the nuclear matter being all smashed together.
yeah, so how do we find out the velocity of it? Like,
How do we,
how do we-
okay, yeah, good point. So what you do, the easiest, let me explain it as simple. So let's say, do you remember like in maybe chemistry or intro physics where you look at a lamp, one of those high voltage lamps, and you put a little prism in front of it and you see the different lines?
yeah.
Okay, so basically you know that element X has a spectral signature with a line in hydrogen, like you remember the hydrogen atom maybe, and has
Yeah.
a spectral line at a certain wavelength. And so you look for the same patterns of wavelengths there. So let me put it, there's two parts to this. One is the matter is being ejected. So we can see actually the matter is being ejected because we see the shift of the pattern of the lines from the rest frame we measure in the laboratory. We see it shifted by thousands of kilometers a second, and that's due to the explosion. Now, light, though, the light itself, that's the stuff traveling. The light itself travels at the speed of light. And in fact, one of the coolest things about the case where we saw both the gravity wave signature and the light signature is they arrived at the same time, because they're both traveling through the same space-time. So which is super cool to me. And it showed that all sorts of really weird theories don't do that. So because light travels at the speed of light, the stuff that's being ejected from the merge of the neutron stars gets ejected at different velocities that have to do with the gravity, what's going on with the merger. But the light that we see that gets, let's say, a photon that's coming from that stuff that travels to us is traveling across space-time at the speed of light. And the perturbation in space-time is too, and they arrived at the same time. So I think that's really cool. And I guess to some extent, the distortion of space-time can distort the wavelengths a little bit, but that is so small. That's 10 to the minus 21. That's not, that's negligible. So in fact, what we see is the light that's traveling along the space-time from there is actually getting redshifted because of the expansion of space-time between that object and us. Depending on by however far away the object is. So that's all the cool stuff. You can always take
Thank you.
astronomy
Thank you so
or upper level astronomy classes, I guess. But I don't think you can because this is me. I don't think you underestimate the coolness of the gravity signature and the light signature arriving at the same time, to me. But that's why I do. That's why I was doing this for decades of my life.
Can I ask you a more theoretical question, I guess?
Sure.
Does the formation of black holes and globular clusters have anything to do with the theory that there's like a supermassive black hole at the center of galaxies and things like that?
No, yeah. So those are both true, but they are different.
Okay.
So the ones in the globular So the challenge is, I can talk about this stuff for a long time. So Arden can shut me up and move me on to other questions. But so we think we know how to get the ones from stars. So it's not, our sun's not going to turn into a black hole. It's not big enough. But if you happen to get those rare massive stars, their centers can get compressed to become a black hole. But that only ends up with like a black hole that's tens of solar masses, 10 times the mass of the sun. But how do you get to the one like the center of our Milky Way that's millions times the mass of the sun? That means you need millions of ones like around our, like a regular stellar one, to all get together in the same place and coalesce. Or you need some other way. And then there's the ones that just aren't millions. We know ones that are billions of solar masses. So it's actually still an somewhat open question how you build up to such big black holes at the centers of galaxies. I don't specialize in that. Professors Voigt and Donahue know some of that better than me. It's not completely 100% understood how that happens, though. But we're sure they're there. But how you build, maybe there's some maybe the centers of the galaxies get so dense they collapse directly to a black hole. Maybe you do manage to get enough coalescence. It's not 100% clear.
Okay, thank you.
Yeah.
I have a quick question.
Yeah,
Do you
sure. Go
know
ahead.
anything about I'm not sure exactly how to pronounce it, but I think it's spelled NYX, that star cluster.
No, yeah, is that I haven't found, no, I don't. I mean, so sorry, I sort of half remember the name, but I don't know anything more about it.
I was looking at this.
Yeah, go ahead.
I
Sorry.
was looking at it for my astronomy class for one of my proposal project we had to do.
Okay.
And it's a star cluster that apparently its origin is from another galaxy.
Oh, okay. Yeah.
Discovered in like 2020 or 2019. So
Yeah, the outskirts of galaxies are not really super far away from each other. So that you can get things like that. And then, I mean, to some extent, galaxies are sort of like each other. So they all have these star clusters. So if one galaxy gets too close to another galaxy, some of its star clusters can be basically torn from one and end up in the other one. And even though the galaxy, the star cluster itself is fine because it's this compact little thing, but it got moved from one galaxy to the other. Yeah, that can happen. It's even true. So our own Milky Way galaxy is going to collide with the Andromeda galaxy in about 5 billion years. So I don't know, but we'll be fine because we're so we're so close to our sun that the overall effect of that is not like, I mean, it could be some subtle ways that it has, but and it's true for the star clusters. They're dense star clusters. Mostly they can change how they're orbiting around their galaxy, but the stars themselves won't really care.
okay, thank you.
Yeah.
I got a question. Do you think that like globular clusters, these overall larger star clusters, are kind of the part of the main contributing reason as to why the galaxy keeps its structure? Because I know like everything orbits around the black hole, but at least from what I've read, it's just not enough gravity to really keep everything together. So do you think that the clusters are actually paying part of that reason?
Yeah, no, they're not enough of a factor. They're just not enough star. So that's where the dark matters believed to come in. So the globular clusters are not there. There's not enough there. Even if they all have black holes in them, they still don't have enough mass to do that. And so the dominant mass component in our Milky Way is unseen, which is why it gets called dark matter. And so these don't change that.
Thank you.
Yeah.
Okay, well, thank you, Dr. Zepf,
Sure, no problem. Glad to do it.
to us. And thank you, everyone, for coming.
Thank you.